Hey, you made it to reading quiz number 40 on separable differential equations. Welcome. We will be talking about one of the primary methods for actually trying to solve our differential equations and figuring out what the initial equation was that we had. So let's get started. A couple of preliminaries. What is a separable differential equation? In this lesson, we will learn how to solve them. The separable differential equation is one where the x and y parts can be separated, go figure, and integrated by each part. So some examples of separable differential equations include, if we had dy dx is equal to y over x, that division will allow us to separate the y and the x part. Dy dx is equal to xy squared over 3, and dy dx is equal to x times y. So typically if you see something with division or with multiplication and you've got an x and y variable, you generally have the chance to separate. Differential equations that are not separable include dy dx is equal to x plus y. We saw that in the lab, and you kind of need different techniques to solve that. Or even something even more complicated like dy dx is equal to sine of xy plus 2x. So we'll take care of the first type, the separable differential equations. Here's an example. So let's say you have this differential equation dy dx is equal to x over y, where y is equal to, or excuse me, y of 1 is equal to negative 2. Find a formula for the original equation. First step that you want to undergo when you're trying to solve a separable differential equation is to separate the variables. So you want everything with y or one variable on one side and x or the other variable on another side. Oftentimes you can do this by cross multiplying. In this case we get y dy is equal to x dx, which allows us to have all the y's, including the dy part on one side, and all the x's, including the dx on another side. Then we integrate both sides, all right? And since we have a y dy, we're integrating with the y variable. You're going to only need to add 1 plus c per side, and the reason for that is, although we do really have 2 plus c's, when you subtract 1c to the other side, you still get a constant. So instead of writing multiple plus c's, all right, we combine that all into 1 plus c to make our lives easier. Step 3, we want to use our initial condition to solve for c. If you remember, I gave you that little tidbit of information that y of 1 is equal to negative 2. I'm not just doing that for laughs, all right? There is a reason for that. We need to plug in our x equal to 1 and our y equal to negative 2. One of the things, if it's written in this format, you got to be very, very careful about which is the x and which is the y. So make sure that you're paying attention to what the input is and what the output is. So in this case, we plug negative 2 in for y and 1 in for x. We get negative 2 squared over 2 is equal to 1 squared over 2 plus c. Solving that arithmetic, we get c is equal to 3/2. Now, this is the last part that kind of makes it a little bit challenging. So we've got plus c, we've got our dy's and dx's out of the way. How do we make this a function? And this is where you also have to pay attention to what the initial condition is. So in this case, when we put our plus c back in, as you can see, we get y squared over 2 is equal to x squared over 2 plus 3/2. Just to make things easier, we'll multiply by 2 on both sides, and we get y squared is equal to x squared plus 3. Solving for y, we technically get y is equal to plus or minus the square root of x squared plus 3. That's a problem. That's not actually a function. We plug in an x value, we get multiple y values out. So this is where our initial condition comes in. The fact that y of 1 is equal to negative 2 means that when we plug in x is equal to 1, we should get negative 2 as our y value. And the way that you can accomplish that is by choosing the negative branch of this parabola. And so we have y is equal to negative square root of x squared plus 3. So be careful there. You might fall for the trap of putting the plus or minus, but you actually really haven't finished the problem because we want to solve for the original function. In example 2, we've got the same sort of procedure. We're using separation of variables to solve dy dx is equal to negative xy squared over 4 as long as y is not equal to 0. And in this case, where y of 5 is equal to 2. So again, we want to separate. We want to get everything with a y on one side of the equation and everything with an x on the other side of the equation. First step would be to say the 4 dy is equal to negative xy squared dx. and then we can divide by y squared on both sides to get 4 over y squared dy is equal to negative x dx. Okay, you might anticipate the next step, we want to integrate. So in this case, we've got 4 over y squared. Remember that that's a y squared on the bottom. All right, if it were a linear factor, we might be able to use natural log for our antiderivative, but 4 over y squared is really the same as 4y to the negative 2, so be careful with that. When we find the antiderivative for that left side of the equation, we get negative 4 over y, and of course the antiderivative of negative x dx is negative x squared over 2, and again we only have that 1 plus c that we need here. Step 3, we use our initial condition. So at the very beginning, we said that y of 5 is equal to 2. We plug in 2 for y, and we plug in 5 for x. So negative 2 is equal to negative 25 halves plus c. So working that out, you get c is equal to 21 halves. Now again, the tricky part is solving for y. You notice that y is in the denominator of a fraction here. All right, so we got maybe a little bit of a challenge to try to figure out how to solve for y. Luckily, we've got the right side of the equation as negative x squared over 2 plus 21 over 2. All right, so we can combine that and write that as 21 minus x squared all over 2 and set that equal to the negative 4y. Well, where can we go from there? We can find the reciprocal of both sides, and we get y over negative 4 is equal to 2 over 21 minus x squared. Or if you prefer to cross multiply, that's fine. We end up with y times 21 minus x squared equals negative 8. And solving for y, we get y is equal to negative 8 over 21 minus x squared. Example 3. So we, in this case, have y prime is equal to x squared times y, with y of 0 equal to 4 as our initial condition. This one is written a little bit differently, but remember the y prime notation in this case would just mean that dy dx is equal to x squared over y. And you'll find it helpful to write the equation that way in order to get your variables separated. So here we get dy dx is equal to x squared y. We can separate the variables as in the previous two examples to get dy over y equal to x squared dx. This is where it pays off to remember the antiderivative of 1 over y. Remember that we wrote that as natural log of the absolute value of y. All right, that'll be very, very key in just a minute when we actually go through to solve the particular solution based on our value for c. We also get natural log of absolute value of y is equal to x cubed over 3 plus c. There are two different ways that you can go with this. I'm going to show you one way that I feel is a little bit easier, but we'll talk a little bit about the other way towards the end. So remember that in order to remove the natural log part and solve for y, we can raise both sides e to the natural log of absolute value of y, and then e to the x cubed over 3 plus c. Now in this case, notice you still keep your absolute value there, and we're going to have to figure out how to address that in just a second. Another thing to note that is that we can rewrite the e to the x cubed over 3 plus c as e to the x cubed over 3 times e to the c. And that'll be very helpful. That's just our exponent laws from way back when. On natural log problems, we're going to make our life easier by introducing a new variable, typically called k. And this will allow us to take off the absolute value, because what we're going to do is we're going to let k equal to plus or minus e to the c, which covers the possibility that y could be positive or that y could be negative. And when we do that, it cleans up the problem really nicely. So we take off the absolute value because we have that plus or minus incorporated into the k, and then we can rewrite the e to the c as just that k. So now our new equation to solve is just that y is equal to k e to the x cubed over 3. Now we can get to using our initial condition. In this case, we have y is equal to 4 and x is equal to 0. We set 4 equal to k times e to the 0, so k is equal to 4. And then, bam, the solution is right there when we plug in our k. So we get y is equal to 4e to the x cubed over 3. Now, this is a little bit different of a problem, and whenever you see the absolute value of y or the natural log of the absolute value of y, this is typically a good way to proceed. All right, so that's kind of your clue when you see that natural log. Okay, we need to maybe try something a little bit easier with this k is equal to plus or minus e to the c, which, by the way, you will have to write off to the side, make sure that you've clarified what you're defining k to be. That's not to say that we couldn't plug in our initial condition up here at the very first part of step 3, or even back at step 2, where we have natural log of absolute value of y is equal to x cubed over 3 plus c. The dangerous thing about that is I know that a lot of students, when they try that method, they forget the fact that the initial condition is positive or negative depending on the situation. And so they end up not putting the right sign and getting a lot of points taken off because their final answer is incorrect. So that's why I say if you make k equal to plus or minus e to the c, you have already absorbed that plus or minus into the way that you solve for your initial condition, and it makes everything easier, and you won't fall into that trap. We can talk more about that, though, when we're in class.